We're going to continue going over our intro to entropy, and we're going to develop a few more sets of equations before we get to the examples. So the next set we're going to develop will be for entropy change of an incompressible system. Now remember, if we say something is incompressible, that means density, which is rho, or specific volume, is going to be constant. And our internal energy, U, depends only on temperature. So pressure won't matter. Only care about temperature. Okay, so that's what we'll have for incompressible. Now, keeping that in mind, if you remember when we originally talked about incompressible and we were talking about specific heat and everything, we said that du equals C times dt. So we developed that equation before. Now, what we're going to do is, if we look at the equation, TdS equals T du plus P times dV, if we look at that and we divide by T, then let's see what we'll get. That would give us ds equals du over t plus p times dv over t. So now we've got that. Now we already know du is c times dt, so we could plug that in right here. So let's put an arrow, I want that to go in there. And then we would have ds equals c times dt over t plus, what about this last term? If you think about it, we said we had an incompressible system. So do we even need this term? Because this is change in specific volume. Are we going to have a change there? Nope, because it's incompressible, so that goes away. So this means ds has to equal the specific heat times dt over t. So let's write that out. So ds is c dt over t. And then if we come down here, no. So now if you look at this, we've got ds equals c dt over t. We've got these two differentials in here, right? How do we get rid of that? What do y'all think? We need to integrate both sides, right? So let's integrate both sides. We're going to go from state 1 to 2 on both sides. Remember, c is a constant, so that pulls out. So once you integrate that, you're going to get S2 minus S1. So this is the entropy at state 2 minus the entropy at state 1. That's going to equal the specific heat times the natural log. And notice this is temperature here, this is dt. So we'll have T2 over T1. So this equation right here is going to give us the change in entropy. All right, and this is specific entropy. These are little s's. Okay, and remember, C is a constant value. Typically, you're given that in the problem statement. This will give us another equation. So basically, it relates our temperature change to our change in entropy. Now let's look at what we get when we have an ideal gas. All right, so from equation 1, and remember, if you look back from a previous video, we had equation 1, that was the set of equations. So if we go back to those, and we divide by T, which is our temperature, then what we're going to get is ds equals du over T plus pressure over T times dV. And in addition to that, we had the two equations, remember? So the second one would be ds equals h over t minus v over t times change in pressure. Now we've got these two equations. Before, when we went through and developed our ideal gas equations, we said that du equals cv dt, and we had dH equals cp dt. And then the last thing we had was PV equals RT. So these three equations we developed before when we were talking about an ideal gas. So now we can use these equations along with these, and let's see what we get when we do that. Plugging all those in, let's look at this first one. Let's just call that 2, we'll call this 3. So from that equation 2, we've got du. We know du is cv dt. Let's plug that in. So we're going to have ds equals cv dt over t. And then the second term, we have the pressure over the temperature. Now, it would be good if we could get this term in terms of a specific volume, because that's what we have here. So if we look over at this equation for the ideal gas, we can solve for P over T, and if you do that, you get R over V. So let's plug that in. So we're going to replace the pressure over temperature with R over V. So we'll have R dV over V. Alright, so now we've got that. Notice we've got differentials in all three of those. That means we could integrate and go from state 1 to state 2. Alright, so that gives us another equation, and we'll write out the final value or final equation in just a second. And notice again we've got dt over t and then dv over v. That makes for really simple integrals. R and cv are constants, so those will be pulled out. From equation 3, we're going to do the same thing. Alright, we got ds, and then for dH, let's replace that with the specific heat of constant pressure times the change in temperature. Put that over t, and then for this one, we've got v over t. So let's solve this equation for v over t. So if you did that, you'll get R over pressure. So we'll have R dP over P. Again, differentials in each term. Notice we've got dt over t and dP over P. That'll make for easy integration. So we're going to integrate from state 1 to 2, like that. Now what you get when you integrate all of that, it's going to be, that's arranged here. All right. So from this first one, you're going to get S, and this is going to be a function of your temperature at state 2 and your specific volume of state 2 minus the entropy, and that'll be at T1 and V1. That's going to equal the integral from T1 to T2 of CV, which again is a function of temperature, times dt over t plus R times the natural log of V2 over V1. Okay, so that's what we'll get for this. And then for the second equation down here, we'll do the same thing. For this one, notice on the right side we've got pressure, or we've got temperature and then pressure. And for that, we'll have the entropy. It's going to be a function of T2 and P2. This was for state 2, minus the entropy at state 1. So that'll be a function of the temperature and pressure at state 1. That's going to equal the integral from T1 to T2 of Cp, which is a function of temperature, times dt over t minus R times the natural log of P2 over P1. So now we've got that. So let's box this. All right. One more thing that we need to recall. Recall the difference between CP and CV at a given temperature is just going to be that gas constant R. Okay, now we're going to look at the ideal gas table. And here's what it looks like. So this is the one for air. Remember, we've got our temperature. We don't have pressure in here, just temperature. We've got our specific enthalpy, our specific entropy, and then we've got this S to the 0, or actually it looks a little degree symbol. This is going to be a new symbol. All right, and let me tell you what that is. So let's move that. So in the ideal gas table, we saw that symbol. So there's that column for the S with the degree. This itself is a new symbol. Okay. And I'll just call it S degree. Now what that is, it's going to be a function of temperature, obviously, because that's what the ideal gas table has. It's just temperature. That is going to be the value of the integral from a t prime, I'll tell you what that is in a second, to t. Then the integrand here is going to be Cp, which is a function of temperature over temperature dt. Now this t prime is an arbitrary temperature. Now, that probably didn't make any sense. So why in the world do we need this? What is this for? The reason why we want these values is because we can use these values when our Cp is not constant. All right, so if it's changing, because sometimes it does change. Now, that being said, let's see how to use this and how it's going to help us. So let's say we want to have the integral going from t1 to t2 of Cp times dt over t. All right, and Cp is not going to be constant, it's going to be changing. Now, with this t prime, what we can do is we can say that this equals the integral from t prime to t2 of Cp times dt over t minus the integral from t prime to t1 of Cp times dt over t. All right, so these two statements are equivalent. Now, these values are in the table, whereas this we wouldn't be able to find otherwise because Cp is changing. So with this, we can say that this left-hand side is equal to the S degree at temperature T2 minus S degree at T1. Now, if we keep that in mind, then if we look at equation 2, actually let's call it something else. Let's call it equation 4. So if we look at equation 4 here, this is the one with Cp in it. All right, so if we go to that one, let's just put equation 4, then becomes the entropy at state 2, which that's going to be a function of temperature and pressure, minus the entropy at state 1. That then is going to equal the values in the table at T2 and T1. You're going to take the difference there. Minus R times the natural log of P2 over P1. So that will allow you to find your change in entropy even if you have a CP value that is not constant. So if it's changing, you don't have to have an equation for it. You can just use this. Instead of trying to figure out how CP is changing, this is a lot simpler. Now, these equations up here assume that CV and CP are changing possibly. If they are constant, then it's easier. So if our specific heats are constant, then what we're going to have is you'll have the entropy at state 2 minus the entropy at state 1. That's going to equal CV, because now it's constant, times the natural log of T2 over T1 plus R times the natural log of V2 over V1. And then we'll do the same thing for the second equation up there. So the entropy at state 2, if we have it as a function of temperature and pressure, subtract that at state 1. That's going to equal CP times the natural log of T2 over T1 minus R times the natural log of P2 over P1. Alright, so that'll give us a couple more equations. So these are only going to be if CP and CV are constant. But now you've got an equation that you can use if you're given a change in temperature and specific volume, or if you're given change in temperature and a change in pressure. This will allow you to find the change in entropy. All right. So let's do an example. Actually, we're going to do 2 examples. And then we'll start getting into how we can apply the concept of entropy. All right, I will see y'all in the next video. Thanks, guys.